All right, it looks like we're recording as always. I can't usually keep up with the chat during lecture. I try and check it afterward. But if you have a question, just unmute yourself and ask it right here in class. Let me know if you can't see the slides or anything like that. Otherwise, let's go ahead and get started. We talked last time about how numbers are represented in a computer system, at least part of the story on that. I reminded you of what you probably knew about how binary numbers work. You remember hexadecimal from C and Software Tools class, so maybe that wasn't anything new, but one new thing you probably saw was how to do basic arithmetic, at least add and subtract for unsigned values, where we didn't have to worry about negative values, only 0 and positive values. And detecting when those operations don't work. We kind of had a motivating example of, it's the one from homework 0, of a program that gets a overflow, and in a lot of higher level languages, there may not be a good built-in way to detect that, or kind of by the time you get to a language at that high level, you end up having to do extra work to detect something that the hardware can help you do automatically. Starting today, we're going to understand how signed numbers work, representations that can store both positive and negative numbers. And certainly sometimes sign matters, whether you're storing just 0 and positive numbers, or you have to worry about also being able to represent and compute with negative values. In even a language like Java, which takes care of a lot of things for you, and often maybe you haven't worried about this, the possibility of things like overflow or how math operations really work. Maybe you haven't worried about that in Java, but it still could be a source of bugs in your programs. In Java, they do math the same way we'll figure out in class today. The way Java represents numbers is the same 2's complement system we're eventually going to settle on. And that means the potential for overflow is there. But there aren't built-in mechanisms for letting you know when this occurs. It's kind of up to the programmer to make sure that they're using a type that has sufficient range, or like I suggested a moment ago, maybe adding extra code to detect when there's a risk of overflow or when overflow is about to happen. So like a lot of things, it's up to us, the programmer, to worry about this kind of thing in our code. You remember in C, even though we're closer to the hardware, C also simplifies how arithmetic is done, at least compared to the underlying machine. And you saw this in C and Software Tools class when we were dealing with potentially operations of mixed type. Pretend this is a fragment of C code and think for a moment, I guess, what you would expect this program to do, or maybe better, what you would like it to do and what it's actually going to do. So here I make a variable u, I put 10 in it, and then I ask, is u bigger than -1 or is u smaller than -1? What's going to happen in this case? Well, I guess since u is 10, it seems like it should be bigger than -1. So I guess I'd say that first output is what I would expect. But in C, if you think about it, here's the output you're going to get. And the reason, I'll give you a moment to think about it if you want to. Why is this going to happen? Well, you could say it's because C thinks 10 is less than -1, but it's really because C simplifies what's going on in the underlying machine. And by that, I mean when it has an expression of mixed type. When you've got variable u that you just said you want that to be an unsigned integer, and you're comparing it against -1, well, even if that wasn't a negative number, if you don't say otherwise, C is going to assume that's a plain old int. But remember, if you do a comparison or you do arithmetic in C that mixes signed and unsigned types, then it converts them all, it converts both of the types Actually, you'll remember it's a little more complicated than that. Let me quickly say, to integer-sized values that are mixed signedness. It converts them to unsigned before it does the math. And the problem is converting converting -1 to an unsigned value doesn't give you what you would like. Maybe it couldn't give you what you would like. We'll talk about what it actually converts to, and we'll understand in more detail what's going on here by the end of the lecture today. Previously, we just had to worry about unsigned numbers. Last lecture, we figured out how an unsigned positional number system works, with special attention to number systems written in binary. Today, we're going to talk about how to handle signed numbers also, and really how we can build, or maybe what makes sense for how we build hardware that works with these numbers. We spent some of our last lecture talking about how the hardware could actually do basic arithmetic operations, add and subtract. And even though we don't know it, at least for this class, we don't get all the way down to how we'd actually build the hardware. We understand what hardware is going to have to do with bits to add two numbers, as long as we don't have to worry about negative numbers. We want to figure out how we could build hardware that also works with negative numbers. Could we do this on the cheap? Could we use the same tricks for doing arithmetic with mixed signedness that we did with just unsigned numbers? So could we take the same add logic that we came up with last time, and could that also work for signed numbers? I guess there's an advantage to being able to use the same kind of hardware for both. It'd make it easier to build the hardware. It would, we could reuse existing hardware instead of having to build two different ways of doing addition. So that might let us build, since the hardware has less overhead, maybe we could do a better job of optimizing that. Of course, if we built specialized hardware to add unsigned values and separate hardware to build signed values, maybe we could take advantage of something pertaining to that, each of those operations, something specific to each of those operations. What if we just tried to do the same logic? What if we tried to do signed arithmetic the same way we do unsigned arithmetic? Well, we could try this out in decimal and see how it works there, since we're more familiar with that. Over on the left, we can pretend those are unsigned values. I picked positive values there, so let's pretend they're a representation that only has to worry about 0 and positive values, and an unsigned representation. Over on the right, we're pretending we have to worry about mixed signedness, or I guess said better, we have to worry about being able to store positive, negative values, and 0. You know how you do arithmetic, same thing we did last time. If you had to add 10 and 15, well, we can take it a column at a time. We add the ones place and we get 5. We add the tens place and we get 1. And I would say handling that a column at a time works correctly if both of the numbers are positive. If we take the same logic and we add up positive 10 and negative 5, 0, just doing the same operations. 0 plus 5 is 5. There's no carry into the next column here, so 1 plus 0 is 1. But I don't know what to do with the next column. If that second number was negative and the first one was positive, I don't know what to put down there to give me a right answer. Certainly putting positive or negative isn't going to give me the right answer in this case. So at least with the obvious way of representing signed numbers, just sticking a plus or a minus out front, we're going to need something smarter, something fancier, or we're going to need to figure out something fancier than just reusing our existing system for adding numbers. And we also have to worry about subtracting and eventually other mathematical operations. What does it take to do math on signed numbers, even if they're in base 10? Well, we can extend our rules. So here, UPN, that's what we mentioned before. we can extend the rule we used for unsigned positional numbers to make it work for signed numbers. So here's a bunch of cases we might have to worry about. It's almost, well, most of them are the same or similar to the previous example, just with different signs floating around. So the first case is easy. If we have to add two positive numbers, we already have a rule for doing that. If we have to add a positive and a negative number, well, positive 10 minus 5 should work out to positive 5. The other way around, negative 10 plus positive 5 should work out to negative 5. Negative 10 plus negative 5 should work out to negative 15. And positive 10 plus negative 10 should work out to 0. And there the point is, for positive or negative, I guess we could tolerate it being called either positive or negative. Or I guess I would say 0 is neither. It doesn't matter whether you, or I would classify it as neither positive or negative. I stopped short of saying you could call it either. I would say for the special value of 0, positive or negative, seems like it shouldn't matter. So we need a rule that gives us this kind of answer, even if our operands are signed and the things we're adding together, and right here we're just worrying about addition, even if the things we're adding together are mixed signedness. Now, two of these examples worked out just like they did when we didn't have to worry about signedness. It's these two here. When I was adding two positive numbers, my result ended up being a positive number. And if I computed it just a column at a time in base 10, the same way we added just non-negative values, I'd still get the right answer. Same with that, I guess it's the third column here. It's the fourth column, unless you're a computer scientist. This column right here where I'm adding two negative numbers. I can still add them up, ignoring the sign, and then the result ends up being negative. So here's kind of the first part of a rule for adding up two numbers in this representation. And we'll call this the signed magnitude representation. You can see it up there at the top of the slide. Signed magnitude just means if I'm writing down a signed value, or if I'm storing a signed value, I'm going to need to store whether it's positive or negative. So that's the signed part. And then I'll need to store how big it is. That's the magnitude part. So signed magnitude representation is here's a number, and here's whether it's positive or negative. So for signed magnitude values, or for signed magnitude representation, if I was going to store signed numbers, positive and negative numbers, as a sign along with how big the number is, what its magnitude is. For adding two values that have the same sign, I can just use my same rule I did from unsigned positional number system. And then just the result will have the sign of the two input numbers. How about these two cases in the middle? If the values are mixed signedness, well, I guess admittedly how I do this is I take away the smaller number from the larger one, or I guess said better, the one that has smaller magnitude than the one who has larger magnitude. So in this case, if I had to compute 10 plus negative 5, I'd figure out how far apart they are, 10 minus 5. And then that's my result. So I would use subtraction for that. And then the sign of the result would be whatever the sign of the larger one is. So positive 10 plus negative 5 gives me positive 5. Same rule here. I figure out which one has larger magnitude. Here, that's negative 10. I take their difference. So 10 minus 5. And then the result has the sign of the larger magnitude number. So it keeps the sign of the negative 10. So that's what's written at the bottom. If they're, yeah, I think this might be an error. Well, sorry, I was going to say it's an error in the slide, but I was wrong. Here, if the signs, backing up, if the signs are the same, here's the rule that applies. So here, if the signs are different, so if they're not the same, they must be different. So if the signs are different, but their magnitudes magnitudes aren't the same. Their magnitudes are different. Take their difference and the result has the sign of the larger value. And that only leaves us the case over here on the right. Their magnitudes are the same. So you're subtracting a number, or you're adding a negative version of a number to a positive version of that number. And then no matter what the magnitude is, they should cancel out and the result should be 0. So that's talking about this last case here. So we just figured out how to build hardware to do arithmetic on a signed magnitude representation. I just claim I wouldn't want to build that hardware. At least that's some of what we're going to do today, is we're going to figure out a simpler way. It'll take a little more figuring out, but a simpler way to do operations like addition if we're willing to represent numbers differently. I guess this is our fallback. If this is the best we figured out, this is at least something we could do. We could build a system where we represent positive and negative values using a signed magnitude representation. And I won't read through it, but backing up a few slides, we'll just need the rule at the bottom of this slide to do addition. If the signs are the same, do this. If the signs are different, but the magnitudes are different, do this. Otherwise, if the signs are different or opposite and the magnitudes are the same, do this. We've been doing this in base 10. We could do this in, if we're really going to do this computationally, we'd do it in base 2, since that's how we're representing numbers anyway. And in a way, this works out nicely in base 2, because we would need a bit to store the sign, and then the rest of the bits would store magnitude. So if you, like the picture shows, if you had a 4-bit representation for a number, and you were going to use signed magnitude, this first bit, we'll say the leftmost bit, the one that would otherwise be the high order bit, we'll pretend it represents sign, maybe 0 for positive and 1 for negative. In fact, even in our other representations, we're going to follow that rule. So 0 here means positive, 1 here means negative, and then the rest of the bits could represent magnitude, just like they did in our binary positional number system. I guess a nice thing about this is as long as the value is positive, it looks the same as it does for an unsigned value. And for negative values, we couldn't represent them in unsigned anyway. I guess there's one problem with this. It gives us 2 ways of representing 0. If you let me back up to this slide, if you had a 0 here in this blue bit and this high order bit, and the rest of them were 0, that would be 0. I guess it would look like a positive 0 because of the 0 here in the high bit. If you put a 1 here in the high bit and had zeros in all the other bits, it would still be worth 0, but it would look like a negative 0. Is this a problem? Well, I guess mathematically, we don't really need 2 different ways of representing 0. If you've got 0 of something, arguably there's no point keeping up with whether it's a positive or a negative 0. Having nothing is the same whether you call it positive nothing or negative nothing. This could be a real problem if we're writing code with it. If you read in a value and you wanted to check if it was 0 or not, if you had 2 different ways of representing 0, 2 different bit patterns that both mean 0, then you might have to check against both of those, which could make our code more complicated. So I'm going to say that's a disadvantage of signed magnitude, at least as a way of representing signed values. That's okay. We're going to talk about 3 different ways of doing that, and I've listed them all here. So the first one we've already talked about. We could represent signed values, so some way of representing numbers that can handle positive and negative numbers. We could represent that using signed magnitude, and we'll see that we've already seen that has some disadvantages. Another way we could go is something called ones complement, and we'll talk about that in a moment. And the way I'll say secretly, the way we're going to settle on, you already know about, because I know we mentioned it in the C and Software Tools class. We said on all modern computer systems, signed values are represented using something called 2's complement. So eventually we'll sneak up on that as a way of representing positive and negative numbers that has some real advantages. When I say advantages, I mean kind of these three things we might want to worry about. And we'll consider this for all three of those representations. How do we do addition? We already saw for signed magnitude, well, it took us kind of 3 slides to talk about here would be a rule for how you could add numbers. So we'd like a way of doing addition that's simple. I guess all else being equal, we'd like just one way of representing 0. So we don't have 2 different ways of writing down 0. And I guess it'd be worth it to think about how many different ways we have representing other positive and negative numbers. Sorry, a better way to say that would be, in our representation, do we get an equal number of positive and negative numbers, or do we get more positive numbers or more negative numbers? And probably secretly what you remember from C class and probably also from Java is in 2's complement, we're going to end up with 1 extra negative value in our representation. So the representation won't quite be symmetric around 0. So for signed magnitude, you already know how this works. We talked about this a couple of slides ago. For representing, let's say we had 4 bits to represent values with. For positive values, they look just like a unsigned positional number system. Talking through these examples, 0, at least positive 0, is in 4 bits, is going to be 4 zeros in a row. 1 is going to be 0, 0, 0, 1. 2 is going to be 0, 0, 1, 0, using exactly the same number system we talked about in the last lecture. For negative values, well, starting from the positive ones, that's easy because a negative value looks just like its positive representation, just with a 1 in the high order bit. So as an example, if positive 3 is 0, 0, 1, 1, then in sign magnitude, negative 3 is 1, 0, 1, 1. So it looks just like positive 3, except it has a 1 in the high order bit. A nice thing about this is negating a value is computationally easy. All we have to do is flip the high order bit, just invert the sign bit. For adding values, I guess, what would it take to add values in this representation? If we just applied our standard rule for adding, if we had, I guess, a representation of positive 1 would look like 0001. We can read it off the table. Representation for negative 1 would look the same, except with a 1 in front. If we tried our standard way of adding numbers in binary, we'd end up with, well, we'd have a carry bit, or adding 1 and 1 would be 0 with a carry. Adding 1 zeros and 0 would give us a 1 without a carry. Adding 0 and 0 would give us 0 with a carry. Adding 0 and 1 would give us 1 without a carry. So if we just added these representations the same way we did an unsigned positional number system, here's what we'd end up with, and it's obviously not right. We can read it off the table. That looks like a negative 2 in signed magnitude. And if we're adding positive 1 and negative 1, our result should be 0. So, and we already knew this. To add these in a way that works, it's going to take a more complicated rule, that one where we first look to see if the signs are the same. And then if the signs are different, we look to see if the magnitudes are the same. So if I had to summarize, we had 3 things we said we cared about for a number system. For sign magnitude, we don't get to use a simple rule for addition. We don't get to use the same rule we used for adding unsigned values. We got two different ways of representing zero, essentially a positive and a negative zero, which I'd say we'd like to avoid. But we do win in the third category. There are just as many positive numbers as there are negative numbers. So it's symmetric around the zero. It's fair to positive and negative numbers. Is this a good idea? Has anyone actually built a computer system using signed magnitude? Sure, it took us a while to sort of settle on the numeric systems that seemed to make the most sense. And in the 50s, there was a computer system built using signed magnitude for representing numbers. But modern computer systems don't work that way. Let me hesitate before we move on to our second contender, one's complement. Any questions at this point? We still have participants here, so I hope everyone is still listening to me. All right, what else you got? One's complement says you're going to represent a negative number by just flipping all the bits. You're just going to turn all the zeros into ones, and you're going to turn all the ones into zeros. I guess said better, if you had a positive number and you wanted to negate it, you would just flip all the bits. So for the positive numbers, they're going to look just like they did for unsigned values. So just like on our previous table, 0 is going to be 4 zeros in a row, at least for a 4-bit number. 1 is going to be 0, 0, 0, 1, and so on. If those are our positive representations, then these are the corresponding negative representations. So if positive 1 looks like 0, 0, 0, 1 in binary, under one's complement, to get negative 1, you just flip all of the bits. You just flip all the zeros to ones and all the ones to 0. So negative 1 would look like 1, 1, 1, 0. And the same for all of these other values. Sorry, I had something else that I was going to say about this system. Oh, sorry. Just like sign magnitude, on this scheme, the high order bit, the leftmost bit, tells you whether it's a positive or negative number. So even with the rule of just flipping all of the bits, if there's a 0 here, that tells me it's a positive number. If there's a 1 in the high order bit, that tells me it's a negative number. How does addition work on one's complement? Well, we can give it a try and see what happens. Same example as before. In one's complement, here's how we represent positive 1. Here's how we represent negative 1. So same as above with all the bits flipped. If we just go through and add all of the bits, it's going to look like this. 1 plus 0 is 1 without a carry. 0 plus 1 is 1 without a carry, and the same for the rest of the bits. So positive 1 and negative 1 add up to 1, 1, 1, 1, which looks pretty good, because that's just another name for negative 0 in this case. But other math operations, backing up, this is kind of a special case. Other math operations don't always work out as nicely. If we took, yeah, I apologize. I think I messed up on this. So it looks like this one works out also. I apologize for building it up in the wrong direction. If we take two copies of negative 1 and add those together using the standard rule for bitwise addition, so 0 plus 0 is 0 with a carry into the next bit. 1 plus 1 or 1 plus 1 plus the carry gives us, or sorry, I said that wrong. Let me try and get it right. 0 plus 0 is 0 without a carry. 1 plus 1 is 0 with a carry. 1 plus 1 plus the carry gives me 1 with another carry. 1 plus 1 with the carry gives me another one with a carry, and that equals to 1100. Well, over on the left, that should be -2. Is it? Well, this is a 2's complement, or sorry, a 1's complement number. So if we want to know, we can see this higher bit says it's a negative value, which is at least right. If we want to know what this is in positive form, we just have to go through and flip all of the bits. And if we take 1100 and flip all the bits, that gives us 0011, which is a +3. So I messed up twice at the start of the example. I won't read through it all again, but you remember back here when I was saying, this example isn't going to work. And then I panicked for a moment and said, oh, wait, this example does work. I was wrong when I said that. This example doesn't work out. Backing up 2 slides, this one did. We got lucky here. But when we take 2 -1s represented as 1's complement values, I messed up here a little bit. I talked through the addition, and the addition gives us 1100, which is -1 plus -1 at least gives us a negative value. But here it gives us -3. And again, we can see that when we flip all the bits to get the positive version of that number. And it shouldn't. It should give us -2. We can fix it. We can make this operation, or I guess said better, it just takes one thing to fix this operation. And here my slide is kind of messed up, but I think the ones posted on our page are probably correct. We have to do one more operation to make the addition work, and that's called the end around carry operation. That's what this blue arrow is supposed to show, but it didn't show up in the right place in this slide. After you do the addition, the way you normally would for binary numbers, if you have a carry out of the high order bit, and that's what this 1 is, it's a carry out of the high order bit. If you take that and add it to put it back in the low order bit position and add it, this will fix the behavior of 1's complement addition. I guess said better, or said more simply, when you add these numbers using the regular binary addition, if you take the carry out of the high order bit, whether it's 0 or 1, and add it back into the low order bit. And so if it's 0, it doesn't actually do anything. If it's 1, it increments the value. Well, in this case, you would see adding 1 to this gives us 1101. Well, that's a negative value. It should be -2. What is it? Well, if it's 1's complement, we just have to flip all the bits. So that gives us 0010. And sure enough, that's a 2. So this end around carry, this extra operation at the end, is enough to let us use the stamp. So here we can see it works in this one special case, but it works in general. Adding this end around carry operation, taking, again, said real fast, a carry out of the higher order bit and adding it back into the low order bit before the add operation is done, that lets us use our standard bitwise addition or a binary addition operation plus this one extra thing. Question? Yes, thank you for the question. Go ahead.
Does this affect the regular type of overflowing we would expect to have normally? Like if you use 2 negative numbers that overflowed past the negative limit, how would it affect with this end around carry?
Here, you can't, so I guess said quickly, we're going to need a more complicated rule for detecting overflow. Because here, we did have a carry out of the higher order bit. We added these 2 1s, and that's kind of where this 1 came from out of the higher order bit. We added that back into the low order bit, and then we got the right answer, but there was a carry. But that carry doesn't indicate overflow. The reason I say that is, well, we added -1 plus -1 and got -2, which is the correct answer. So what you could do for detecting overflow is if you add 2 negative numbers and you get a positive number, then you must have overflowed. If you add two positive numbers and you get a negative number, you must have overflowed. So you can look at the result, you can look at the sign of the result and see if overflow happened, but just looking at the carry bit out of the high order bit won't help. Now you could, I'll say this real fast, although you didn't ask it. You could say, well, what if you propagate this carry through, you get the carry bit, you add it back into the low order bit, and then you get another carry out of the high order bit when you do that. And fortunately, that can't ever happen. You don't have to worry about that happening. You might get some propagation when you add in that low order bit, but it'll never result in another carry out of the high order bit. Did I answer your question at some point in there?
Yes, thank you.
All right. In summary, now we got two systems for representing signed values. We got signed magnitude, which has actually been used. We've got ones complement, which has a pretty simple rule for addition. It's almost the same as adding unsigned numbers, plus is extra end around carry that we were talking about. So it still has a pretty simple rule. I guess computationally, this would be a disadvantage because you have to do all the work of a regular addition and then some extra work at the end, which could make it a little bit slower. Oh, and just like signed magnitude, we have the same number of negative and positive values. I guess we also have we have the same disadvantage. We've got two ways of representing zero. I'll back up a few slides so I can show you that. It was right here on this table. We got a way of representing zero that's all zeros, and all ones is another way of saying zero. And even though that's what lets us have the same number of positive and negative values, I would say, again, two ways of representing zero is probably a bad thing, not a good thing. Has this ever been used? Sure, in the 60s. The PDP-1 used ones complement, and you can see this makes a lot of sense. Other systems after that also used ones complement. Computationally, a lot simpler than plain old signed magnitude. But it's not used today, at least not on modern computer systems, because we got a better way of doing it, at least a way that simplifies some operations even more. And like I've said a couple of times, it's called two's complement. How does two's complement work? It's a lot like one's complement. Here's a way of describing it. Let's say you had a D-bit representation. So you're going to write down binary numbers using D bits. So D could be 16 if you're going to work with 16-bit numbers, or 32 or 64, depending upon how big your representation was. So I guess as an example, if you had a 4-byte integer, 4 bytes is 32 bits, so D would be 32 in that case. Under the two's complement representation, if you had some value n, and you add what we'll call the two's complement of n to n, it gives you 2 to the d. Two's complement is going to be our way of thinking about the negation of n. So even though this formula doesn't really say that, it says it kind of down at the bottom, but n is going to be our way, think of that as a binary number. Two's complement of n is going to be our way of representing negative n. It's going to be our operation that turns n into its negation. N plus its two's complement gives us 2 to the n. I think this is on a later slide. Sorry, I said gives us 2 to the n, gives us 2 to the d. If you have a 32-bit number, that's a 1 with 32 zeros after it. Maybe a smaller example would make this easier to think about. If you had a 4-bit number, then 2 to the d would be 2 to the 4. That would be a 1 with 4 zeros after it. So any value plus the two's complement of that value adds up to 1 with a bunch of zeros after it, where a bunch of zeros is really however big your representation is, d bits worth of zeros. This is going to work out nicely because if you've got a d bit representation, 2 to the d, well, that 1 bit is off the high order end of your representation. If you've got, like I said, pretend you were representing numbers with 4 bits. Well, 2 to the d is bigger than you can represent. It's a 1 with 4 zeros after it. And this representation is going to give us this behavior, which is kind of nice. N plus the 2's complement of n, that's going to be our way of negating n, is effectively going to evaluate to 0. Now, the formula over there says it's going to evaluate to 2 to the d, but if 2 to the d is 1 with d zeros after it, that 1 is, I'll say it's going to be like overflow. It's going to be a bit that we don't even have room to store. So if you can only store d bits, then n plus the 2's complement of n plus, for us, negative n, will add up to 0. I've got some examples that show off kind of what I was talking about. So n plus the 2's complement of n, formally, that's going to add up to 2 to the d. We want it to behave like n plus the negation of n equals 0. Well, 2 to the 0 is 1. 2 to the first is 1, 0. 2 to the second is 1, 0, 0. 2 to the third is 1, 0, 0, 0, and so on. So 2 to the d is 1 with a bunch of zeros after it. Like I said, where a bunch is d zeros. If you're representing numbers as d bit values, my slide doesn't line up quite right here, then if you're representing numbers as d bit values, you've got room for d bits, then all d of those bits are going to be 0 whenever you add up a number with its 2's complement. That 1 is going to be off the end of the representation. It's going to effectively be, like I said a moment ago, a carry out of the high order bit. Questions before we move on? So I've tried to define how 2's complement is supposed to work, and I've tried to give a little intuition about why. This up here, this top line, you can think of as that's a definition of 2's complement. N plus the 2's complement of n should add up to 2 to the d. And if d is the number of bits we've got in a fixed bit representation, a fixed number of bits, this is the behavior we should get out of that. D, n plus its negation should give us 0. Questions at this point?
So if you were adding up a 4-bit number with what was supposed to be its complement, which would be negative, you intend to end up with 5 bits, which ultimately drops the top bit off.
Yeah, I don't know if I would say it like that, but it sounds like you're thinking the right thing. For this to work, when we add a number and its negation, the operation, the bitwise operation of doing that add is going to end up with a carry out of the high order bit. Does that carry represent overflow? We'll have a new rule for that in a moment, and that rule is going to say that carry, it happens, but it doesn't indicate that you have overflow. We'll have another rule for detecting when overflow really happens. So think of that carry out of the high order bit as that's just part of how 2's complement is made to work, at least whenever you're adding a number and the negation of that number. Other questions? All right, so same idea I was talking about before. So the definition of 2's complement is up there at the top of the slide. If you wanted to compute the 2's complement of a value, well, you could rewrite that definition to say, all right, if I've got n and I want the 2's complement of n, and I know how many bits I'm working with, then all I have to do is take 2 to the d minus n. So if I'm working with a d bit number, the 2's complement of n is 2 to the d minus n. And I know how to do bitwise subtraction, so I can compute that. Notice, though, that this means that the 2's complement representation of a number, or at least complementing it using the 2's complement operation, depends on how many bits you're working with. You need to know if you need a 4-bit result or a 16-bit result in order to do this. We can take an example. So if d is 4, kind of like I've been saying, if you're going to represent numbers using 4 bits, then the 2's complement of n would be 2 to the d. Well, that's 1 in binary. In binary, that's 1 with 4 zeros after it, minus n. We can use this to make a table a lot like the one we made before for those other representations. So let's say we came up with a binary representation for some positive numbers. Same representation as our other two, as sign magnitude and 1's complement. In fact, all 3 of our number systems are going to use the same technique for representing positive values. We already saw that with 1's complement and with sign magnitude. 2's complement is going to use the same trick. So this is how you write down a 0 in binary. Here's how you write down a 1. Here's how you write down a 2, and so on. Same as the previous slides. How do we do negative values? Well, if we wanted -1, we just said how to do that. We can take, if we're doing 4-bit representations, then this is 2 to the d. This is 1 with 4 zeros after it, minus 1. Well, to do that, we have to do a borrow. We know how to do that. And I think my columns, I thought I fixed all of these before class. Maybe I didn't save this to the right file. But this is, I'll sneak in and make sure the posted slides for this, the one that are kind of 6 to a page, I'll make sure those line up correctly. And if they don't, I'll go in and fix that. But this should be our way of doing a borrow in binary. So really this one ought to be over here on top of this one. I think it's just a font problem with the slide. All right, so we borrowed from this one. So we want to subtract 0, 0, 0, 1 from this. And now we can do that. 1, 1 minus 1 gives us 1. And then for the rest of the bits, 1 minus 0 gives us 1, 1 minus 0 gives us 1, and so on into the next bit. So this is 2 to the d minus 1 gives us 1, 1, 1, 1 as the representation of -1 in binary. So if we put that in our table, that is the 2's complement representation for -1. We can continue. If we wanted to know how to negate 2, well, that's, if we're doing a 4-bit representation, that's 1, 0, 0, 0, 0, minus the representation for 2, 0, 0, 1, 0. That gives us, here we also have to do a borrow when we subtract this 1 from 0. And again, I apologize, my columns are not lining up here. But if we carried this out correctly, this should be 1, 1, 1, 0 for this top number, 2 to the d, 2 to the 4, minus the binary representation for 2. So this is the 2's complement representation for 1. And we could continue doing this. We kind of got this way of computing 2's complement based on its definition. To say that real fast, we said, well, if n plus the 2's complement of n is supposed to evaluate to 2 to the d, we just rewrote that and decided how to compute 2's complement via a subtraction operation. But there's a shorter way to do it. And most people, this is how they think of doing the 2's complement operation. And it'll make our next 2 elements of the table easier to fill in, because we get the same result if we just flip all of the bits and add 1. So it's a lot like the 1's complement operation with that extra +1 at the end. We'll do this to fill in the next 2 elements of the table, just to get some examples of how 2's complement works. So rather than having to do this as a subtraction problem, if we wanted to know the 2's complement of 3, well, 3 is 0, 0, 1, 1. So -3 would be flip all the bits, that's 1, 1, 0, 0, and then add 1, that's 1, 1, 0, 1. So that goes in the next spot in our table. If 4 is 0, 1, 0, 0, then flipping all its bits, we get 1, 0, 1, 1. Adding 1 to that, we get 1, 1, 0, 0. So this is our representation of -4 in 2's complement. And we've got room to fill in some more of these in our table. Using 2's
So
complement. Yeah, go ahead.
just a comment. So with 2's complement, is the first digit always going to, if it's negative, is it always going to be 1? And if it's positive, it's always going to be 0?
Yes, you're right. I haven't said that, but it's going to follow the same rules, or at least it's going to give us the same thing as our previous number systems. If the high order bit, the leftmost bit is 0, then we'll say it's 0 or positive, since that's true for this guy up here. If the higher order bit is 1, then it's a negative number in 2's complement. This operation is invertible. And it makes sense that it should. What if you started with a negative value, like you took -2, and you applied 2's complement to it? Well, I'd like that. If 2's complement negates a value, I'd like it to work the other way too. So if I took the bit pattern for -2, that would be 1, 1, 1, 0. If I flip all those bits, that gives me 0, 0, 0, 1. And then if I add 1 to that, I get 0, 0, 1, 0, which sure enough is the bit pattern used for 1. So this works for making a positive number negative or making a negative number positive. So we can do the same operation computationally to negate a value, whether it's negative or positive. What's it take to add numbers in 2's complement? Well, we can try the way we would add numbers for a positional number system, for a regular unsigned positional number system. Let's take an example, +1 and -1. Well, we can read them off the table. +1 is 0, 0, 0, 1. -1 is this guy right here, all ones. If we add those, well, 1 + 1 is 0 with a carry. 0 + 1 with a carry is 0 with another carry. Same thing for the remaining bits. So these will all add up to 0, 0, 0, 0 with a carry out of the high order bit. If we just look at those low order 4 bits, the ones that fit, if we're only working with 4-bit numbers, the ones that fit, that's the right answer. -1 plus +1 gives us 0, and it should. And the reason I keep saying if we're only working with 4 bits or if we're only working with 16 bits is internally, that's how our processor is going to work. It's going to be representing values using a particular number of bits. And once it's done a computation, it's going to have to store that value in a particular number of bits. How about another example? Here we're adding +1 and -1. How about if we add 2 negative numbers? Well, 2 copies of -1 look like 1, 1, 1, 1, and another copy of that. If we add these up, 1 + 1 is 0 with a carry. 1 + 1 + 1 is 1 with another carry. 1 + 1 + 1 is 1 with another carry. Same thing for the next digit. We get a 1 carried out of the higher bit. Again, this doesn't line up quite where it should up above this. But that 1, 1, 1, 0, well, sure enough, that's the 2's complement representation for -2. And that's what -1 and -1 should add up to. So at least for these examples, it looks like we can add numbers just like we did for unsigned values, just a bitwise addition. What else could we check? Well, +0 or plain old 0 is represented as 0, 0, 0, 0. What if we compute the 2's complement of that? Well, under this scheme, we've only got one representation for 0, so I would like that to work out to 0. what happens? Well, if I take four zero bits in a row and I apply 2's complement to that, complementing all those bits, I got 4 1s in a row. Adding 1 to that, I get 0, 0, 0, sorry, I get 0, 0, 0, 0 with a carry out of the high order bit. Questions at this point? So the good thing is, for adding numbers, we get to use the same rule we got for unsigned, or that we came up with for unsigned values, which means our hardware for doing addition can be comparatively simple. When we started with signed magnitude, we've had all of these ifs that, well, we had several ifs to decide how to do the addition. When we did 1's complement, we had that extra carry operation we had to do at the end. Here, it looks like we don't need any of that. We have the advantage that well, it depends on how you look at it. Arguably, we have the advantage that there's no explicit representation for a -0. There's just one representation for 0. And if you had to call it positive or negative, you'd probably call it positive because it has a 0 in that harder bit, just like all the other positive numbers. But having just one representation for 0 means, well, if you've got an even number of bit patterns, and for any binary number, you're going to have an even number of bit patterns, it means one of those is going to fall on one or the other side of 0. So you're going to have an extra value on one side or the other. If we just take, to make the example small, if we just take 3-bit values in the 2's complement representation, then for positive values, we got 0. Well, for non-negative values, we got 0, 1, 2, and 3. And then the next bit pattern would be 1, 0, 0, which would be a negative value according to 2's complement. In fact, that would be -4. This one would be -3. This one would be -2, and this one would be -1, like we're showing here. And this is, like you've seen probably since you took your first Java class, the standard way of representing signed values in Java or just about any modern computer system gives you one extra negative value, which means we've got some asymmetry around 0, and we got one special case for overflow that we otherwise wouldn't have to worry about. What I mean is, if you take +3 and you negate it, you get -3, which is what you'd expect. Same thing for any other value. If you take 0 and negate it, you get 0, except this value down here. If you apply the 2's complement operation to -4, there's no +4. So that's going to be an example of overflow. There's one potential for overflow that can happen just by negating a value. And I know we talked about that at least briefly in C class. Yeah, I apologize. This is kind of talking about some of what we just talked about. If you take 0 and you subtract 1 from it, well, the 2's complement representation for 0 is 0, 0, 0. The 2's complement representation for +1 is 0, 0, 0, 1. If you just did bitwise subtraction from that, you're going to have to borrow just to subtract this 0 from the low order bit. In fact, you're going to have to borrow out of the high order digit, or you're going to have to borrow into this high order digit. Your result's going to be 1, 1, 1, which at least is what numerically you should get. 0 minus +1 should give you -1, and sure enough, that 1, 1, 1 is the representation for -1. This is what I said a slide or two ago. All of our values have negated values, except for 0. -0 is the same thing as +0. And for that one value, -4. For in general, for our largest negative value, we negating it gives us overflow. I'm hesitating because I'm trying to remember what I'm trying to show in the slide, or what I'm supposed to be trying to show in the slide. Yeah, I apologize. I don't remember. Same thing that we talked about before for all of the languages you've worked with. In Java, the range for signed values gave you one extra negated value. The smallest type we've got for numbers in Java, the byte type gives us, it's a signed type, so it gives us from -128 to +127. This is kind of what we've just been figuring out for, if we compare this to our previous number system, I guess the place where it really wins is the rules for addition are really simple. We can use the same rule we used for positional number, for unsigned positional number system. We've only got one way of representing 0, which I would say is mostly good. But we got one extra negative value compared to positive values, and one potential way we can overflow. How popular is 2's complement? Well, I've kind of given this away already. Modern computer systems all use 2's complement. The C standard, you may remember we said this a few times in C and Software Tools class. The C standard doesn't actually say you must use 2's complement for signed values. For unsigned values, it represents them just like we talked about last time. In fact, the C standard guarantees that. But for signed values, when it's got to represent negative, the standard doesn't actually guarantee that, even though on any modern computer system, that's what you can expect to see. Questions before we talk about maybe our one last topic or two? Backing up a couple of slides, I apologize that I kind of messed this part up. I'll take a look at this, and if there's something important that I overlooked in what I should have talked about on this slide, I'll record it in a short video and post that after this lecture. I feel like the main point that's being made here is that we end up with this one extra negative value. Someone already noticed that the way 2's complement works, when you add positive and negative numbers, you get a carry out of the higher bit. At least when we added +1 and -1. We can carry out that operation just like we did any other bitwise operation, just like when we were adding numbers in unsigned representations. But we did get a carry out of the higher bit. It's just that didn't always indicate overflow. Overflow can still happen with 2's complement. It's going to take a more sophisticated rule to tell when it happened. There are really two ways we can detect overflow. The first one is kind of what we already said. It's an intuitive rule. If you're adding two numbers and they have the same sign, then overflow is overflow is possible. For instance, if you've got two big positive numbers, you could end up with or at least the result could be a number that's positive, but too big for you to represent. Same thing with two negative numbers. Here, for instance, if we take +2 plus +2, and let's pretend we've just got a 3-bit representation. So +2 is 0, 1, 0. If we add another copy of that +2 to +2, that works out bitwise. And again, this doesn't line up, but 0 plus 0 gives us 0. 1 plus 1 gives us 0 with a carry. 1 plus 0 plus 0 gives us a 1 without a carry. This carry should be over top of this column. We didn't have a carry out of the higher bit, but that's clearly an overflow because that's -4 in 2's complement. And 2 plus 2 should not evaluate to -4. So we had an overflow, and like we said, just having a carry out of the higher bit doesn't necessarily represent overflow. You and I can tell that there's an overflow here because the answer's wrong, and especially because it has the wrong sign. Here, if you add 2 positive numbers and you get a negative number, then something went wrong. You must have had an overflow. Same going the other way. If you have 2 negative numbers and you add them and get a positive result, then overflow must have happened. If you have 2 numbers with the same sign and the result gives you a different sign, then overflow happens whether you're adding 2 positive numbers or 2 negative numbers. If you're adding mixed signed values, like a positive or a negative, a positive and a negative number, then overflow can't happen in sign magnitude. An informal argument would be if you're adding a positive number and a negative number, the result must be somewhere in between. And if you could represent the 2 numbers that you're adding in 2's complement, you can certainly represent some integer value in between. So we really only have to worry about overflow in this case, where we're adding 2 positive numbers or 2 negative numbers with the same sign in general. So this is kind of our intuitive way of detecting overflow. If you wanted to build this computationally, or if you wanted to build hardware that could detect it, there's another way of checking it. We saw that the carry out of the high order bit doesn't necessarily indicate overflow. Kind of like, when we were doing unsigned arithmetic, when you carried out of that higher bit, if you had a carry out of the higher order bit, that meant you ran out of bits or you didn't have enough bits to compute the result. That by itself doesn't indicate overflow for 2's complement, but if you check the carry into and out of the higher order bit, they have to agree. If they don't match, then you must have had an overflow. And that has secretly been happening in the cases that we've seen so far. Again, my columns don't line up here on my slide, but if you do this case we did before, it's the case where we saw overflow, +2 plus +2. Now those, we can represent that as a 3-bit 2's complement number. But if we add it, we get overflow. We can notice that by just looking at the carry into and out of the high order bit. So talking through it, 0 plus 0 is 0 with no carry. 1 plus 1 is 0 with a carry into the high order bit. So that carry is this one up here. 1 plus 0 is 1 with no carry out of the higher order bit, or with a carry of 0 out of the higher order bit. So there, the carries didn't match. The carry into the higher order bit, this 1, is different from the carry out of the bit, and sure enough, that was a case where we get overflow. You can use either to detect overflow you can use either rule. In fact, you can use both to kind of make sure you don't accidentally make a mistake. To detect when overflow happens when you're adding numbers in 2's complement. Questions? Last time.
That sounds straightforward enough.
Good. I started to say last time, just to show off, we showed that you can do arithmetic directly in hexadecimal. Computer systems don't really do this. Hexadecimal is just for us humans to write down binary numbers, so they don't take a huge amount of space. Computers are good at storing ones and zeros, so when they do arithmetic, they do it bitwise. But for us, we could do arithmetic in this larger base. I know last time when we did it, we kind of cheated by always converting to base 10, at least when we were adding 2 hexadecimal digits. Here, if I gave you two 2's complement numbers in hexadecimal, 0, 5, and FF, if you added them, you could do that. It's just, I'm showing you this to show there's one potential mistake, at least in how you think about this. If you added F plus 5, well, that would equal to 4 with a carry out of that bit. I guess you can think of this as F is kind of like 9 in hexadecimal. It's almost, well, it's 1 less than the base. So when you add 5 to it, you get 4 left over in that column, plus a carry into the next column. And then 1 plus F, the carry of 1 plus the 0 plus the F gives you 0 with a carry out of that column. Well, here you get a 1 carried into that topmost column and a 1 carried out of that topmost column. So you might think that means there was no overflow, but that's because we're looking at it a whole hex digit at a time. Here, well, this 5 is a positive number. The reason I say that is if we looked at it in binary, this 0 here is really 4 bits worth of zeros, 0, 0, 0, 0, and this 5 is 0, 1, 0, 1. So that high order 0 means this is a positive number. Down here, this is a negative number because it's got a 1 in the higher bit. That F here is really a 1, 1, 1, 1. In fact, in general, if you're looking at a number in hex, if its leftmost hex digit is 0 through 7, it's got to be a positive number. Otherwise, if it's 8 through F, it's got to be a negative number. Here we're adding positive 5 to negative 1 to FF. And if we sorry, I'm hesitating here because I don't know if my example is working the way I wanted. The point I'm trying to make, and I'm not sure my example is doing a good job. I apologize, I'm looking back at my example. Yeah, I don't know if my example shows this off, but when you're looking for overflow in a 2's complement addition, if you're doing that in hex, you're not concerned about carry into and out of just the high order hex digit. You're really worried about just that highest order bit. To check that, you can do the addition in binary. You can think about the binary representation of that hex digit, or you can use that other rule that we talked about for checking the sign. The reason I'm hesitating is I thought this example was trying to show that off, but I'm not sure it really is, because it looks like if we take positive 5 plus FF, FF is negative 1 in 8-bit hexadecimal. And it looks like in this case, we get the right result. It makes sense. We didn't get an overflow there. It's just I thought this case was trying to show that off. I've just got a couple of minutes left, but I just have a couple of slides left to show the one other nice thing about 2's complement representation, and that is it gives us an easy way of doing subtraction, or I guess if we were building the hardware, it gives us 2 choices for how we can do subtraction. We talked last time about how we could build hardware that actually does subtraction, kind of like the rule for addition. We can add bits individually, borrowing where we have to, whereas addition carries where it has to. Or we could do this. Instead of, and we mentioned this at the start of our last lecture, if we had to compute A minus B, instead we can compute it as the addition using the 2's complement operation. So A minus B would really be, at least for sign values, should be the same as A plus B, that over bar, the line over B, indicates all of B's bits flipped. So the bitwise complement of B plus 1. So those two parts are the same as what you would do for the 2's complement operation. If you want, so it's kind of like we're saying to compute A minus B, it's the same as A plus the 2's complement of B. Looking at the left-hand side, if we wanted to compute A minus B directly, like I said, we could compute that using the same rules we did last time. 0 minus 1 is, well, we're going to have to borrow, but it gives us a result of 1. We borrowed into this bit, so that leaves us with a 1 minus 0 gives us a 1. We borrowed out of this, or we borrowed from this bit. So 0 minus 1, we're going to have to borrow from the left. So that gives us a 1. And we had to borrow into this bit when we were borrowing for this bit. So 1 minus 0 gives us a 1. We could compute that directly, or it might be easier to do what I've got on the right. We could take A plus B with all of its bits complemented plus 1. So again, these two parts are the same thing you would do in the 2's complement operation. If we add up those three, it should give us the same result as doing the actual subtraction, but we only have to do an addition operation here. In fact, it's an addition with a carry into the lowest order bit. You could think of this one as starting with a carry into the lowest order bit. If you're going to do subtraction like this, it's important that you implement it by adding these three values, or adding these two values with a carry into the low order bit. As opposed to what? As opposed to computing the 2's complement of B and then adding that. And the reason for that is for detection of overflow. If you do it this way, you can apply the same rule for detecting overflow. If the carry into the higher order bit is different from the carry out of the higher order bit, then an overflow happened. Whereas if you just 2's complement B first, there's a special case where you might miss the overflow, or where that rule doesn't work for detecting overflow. So to do subtraction, you can either build hardware to do it directly, or you can you can do it with addition, A plus the complement of B plus a 1, or plus a carry into that lowest order bit. Same thing that we're talking about before. The nice thing about this is we could do subtraction without having to build separate hardware for this. We're just about done. If you return to that first program that we looked at, this kind of explains why a C program might think 10 is greater than -1, and it's really because of this -1. -1 is represented as 2's complement. It's represented as all 1 bits. That's what we've seen in all of our other examples. And if you think of this as a 16-bit value, if you did the 2's complement operation on it, you would see it's represented as FFFF. And if you think of that as an unsigned value, since you're comparing it to an unsigned value U, well, 10 isn't greater than FFFF. So it's going to think this is true, whereas really we think this should be true. I overspent my time a little bit. I apologize for that, but we did finish up our stack of slides with some hesitation. I'll go ahead and stop the recording, but if you have questions, hang around and I'll give them a try. And like I said, I'll go back and see if I want to record a minute or two of the material that I messed up on earlier today. Thanks for your attention and patience. I'll see you next Monday. Have a good weekend.
Thank you. Have a good weekend.
Have a good weekend.